Okay, so in the previous video, we did this calculation where we saw that, if we're talking about electrons moving fairly fast, 1% of the speed of light, we get, something that's on the order of atomic scale in terms of diffraction, or the wavelength that we observe. And so we can actually observe diffraction with electrons. And so that's the next topic we'll be talking about is, experimental observations. So if we scroll down here to where I have some pictures. So this is an image of electron diffraction. And so this is actually it's an experimental technique that we now use to measure atomic scale things because the electron wavelengths are on the order of atomic scale things. So we have some sort of source, an electron gun, that produces electrons at a specific speed. We have a thin graphite screen that is, say, what we're trying to measure, usually. So we're trying to measure the distance between atoms in a crystal or something like that, or in this case, graphite. And so here, we have individual electrons being emitted from this electron gun. But once they pass through this graphite screen, it acts as a diffraction grating for these electrons. So because of their wave-like nature, they interfere with each other. And we see an interference pattern that shows up on this detector at the back of this evacuated tube. The electrons go through, they interfere with each other, and we see something that looks like this on the right. So we see rings where it's bright. So that's constructive interference. Of the waves of the electron. And we see areas where it's dim, and this is destructive interference. And so this combination of constructive and destructive interference produces this pattern, and this pattern is related to the distance between the atoms in the graphite or whatever else we're trying to measure. And so electron diffraction is a very commonly used technique nowadays to measure crystals, to measure structures of crystals. X-ray diffraction is another one. All right, so neutron diffraction can also be used. So we take advantage of the fact that these particles are actually waves as well. When they're moving at a specific speed, we can measure their wavelength. A more dramatic example of this, and one that's near and dear to my heart, because it's a molecule I studied in graduate school, is it's been shown that this even works for something as large as C60. So C60 is a molecule known as Buckminster fullerene. This is the structure of it here. It's basically shaped like a soccer ball with carbon atoms at all the vertices. And so this is a heavy molecule, right? It has a atomic mass of 720 atomic mass units, or Dalton, however you want to say it, right? So compared to an electron, this is massive, right? Or even to a neutron or whatever else. But there was a group several years back, I think in the 90s, if I remember right, that actually showed that you could do the same sort of thing with the electrons that we showed with C60, that you can observe diffraction of these large molecules. And so this was the experiment that they set up. You have an oven. C60 requires very high temperatures to be turned into a gas. You can't observe this in solid C60, of course. It needs to be in the gas phase. But you produce a bunch of gas phase C60, and you send it through these collimation slits. This just turns it into a beam of molecules, so that you kind of have a single source you're looking at. And then they created a diffraction grating with the spacing between the slits and the diffraction grating being on the order of the anticipated wavelength of C60, if you use the de Broglie formula that we just did. And then at the end, they have a way of detecting the C60. So they use photoionization. So they send basically a laser at it to kick off electrons, turn it into an ion, and then detect the ions back here. And they can move this photoionization stage around to observe, how many C60 molecules are they observing in different areas of space, right? Is this, you can move left and right, up and down to observe the pattern here. Or I guess in this case, just left and right. And so when they actually did this experiment, which is shown here, this is what it looks like all set up. And I love the captions here. This is from the researchers who did this, is from their website. So they have their collimation diffraction. They're kind of showing all the different parts that are in that figure above. And then, of course, you have the one who actually did all the work, Olaf, the graduate student there. And so they showed what you get with and without the grading. So without the grading, if we look at the bottom here, without the grading, we just see a single peak, right? So that's just all the C6D molecules collimated into a specific beam. They come in a specific position. And as they move their photoionization stage left and right, they just observe that one peak. But when they do have the diffraction grading present, they observe peaks, right? Multiple peaks. And this is, again, the constructive and destructive interference that's happening because these molecules are actually behaving like waves, diffracting and interfering. The wave nature of these molecules are interfering with each other. And so this is a really dramatic example of something much larger than electrons that shows that this really does happen for for even fairly large microscopic objects. And so this postulate that de Broglie came up with in the early 1900s has been proven to be true and is used for experimental, in terms of electron diffraction, used for experimental results, and then even works up to things as large as C60, which I think is really, really fascinating.